Imagine you have like a single solid 10,000-pound boulder,
Okay.
and you ask a computer to figure out how to fit it perfectly into a 5,000-pound moving truck.
Which is, I mean, by the laws of physics, completely impossible.
Exactly. It's totally impossible. But what happens when that computer just silently smiles, hands you the keys, and pretends it actually worked?
Well, it creates a foundational crack in whatever system relies on that computer. You end up, building skyscrapers on top of a sinkhole, mathematically speaking.
Right. And that silent smiling failure is the core of our deep dive today.
It really is.
We are looking at a really fascinating stack of sources, specifically a detailed academic slide deck and some incredibly striking visual diagrams.
Mm-hmm.
The presentation is titled The Hypergraph Partitioning Showdown, Benchmarking Algorithm Integrity and Safety. And it was put together by a researcher named Look036 from the year 2026.
Yeah, it's a remarkably thorough piece of work. The author manages to take this highly specific corner of computer science and, use it to expose a massive vulnerability in how modern research is actually conducted.
Now, I know what you, the listener, might be thinking. Benchmarking algorithms for scientific computing. It sounds like the kind of topic you'd need like 3 PhDs to even look at.
It does sound a bit dense at first glance.
Yeah, totally. But I promise you, the actual story here is a gripping whodunit.
It really is.
It is a story about scientific integrity, hidden flaws, and the absolute danger of trusting black box systems to do our thinking for us. Okay, let's unpack this.
Well, to really grasp the drama of this showdown, we first need to understand the arena. The entire document revolves around something called hypergraph partitioning.
Right.
The author actually opens with this great quote: divide and conquer, partition your hypergraph, partition your problems, ancient algorithmic wisdom.
I love that. Ancient wisdom applied to cutting edge tech. But let's, build a bridge here for those of us who don't dream in code. I understand a standard graph, like a map of cities connected by highways. A line connects point A to point B.
Right, but a hypergraph is more complex because a single hyperedge the line essentially can connect 2, 3, or even like 100 vertices all at once.
Oh, wow. So it's not just a straight line.
No, imagine a group chat. Sending one message connects you to 50 people simultaneously.
Got it. Okay.
The goal of hypergraph partitioning is to divide these interconnected vertices into k equal parts, say 2 halves or 4 quarters, while cutting as few of those connecting group chat threads as possible.
Why go through all that trouble, though? I mean, what is a real-world application that makes this so vital?
Well, it is the invisible backbone of massive technological applications, most notably VLSI.
Which is what exactly?
That's the physical design of microchips. A modern microchip contains billions of transistors. You can't physically lay them out in one giant block.
Because of the heat.
Heat, yes, and signal delays. It would just ruin the chip. So you have to partition the logic into distinct physical blocks on the silicon.
Ah, so the transistors are the vertices, and the microscopic wires connecting them are those hyperedges.
Precisely. And every time a wire has to cross from one partition block to another a cut, it slows down the processor and consumes more power.
That makes sense.
So the software is tasked with dividing billions of components into perfectly equal physical blocks, minimizing the wires that cross the borders.
And it's used elsewhere too, right?
Yeah, heavily in machine learning workloads and massive parallel computing, where you distribute a complex simulation across, thousands of processors.
That makes the stakes incredibly high. You can't just dump 99% of the transistors into one block just to avoid cutting wires.
Right, the chip would literally melt.
Which just brings us to the fundamental rule these algorithms must follow: the balance constraint. The parts have to be balanced.
Yes. And this is where we get into the actual mechanism of how these programs work. They don't just guess blindly.
They use a mathematical parameter called epsilon, right? Represented by the Greek letter epsilon.
Exactly. Epsilon is the strict boundary line for allowed imbalance.
The sources map out this epsilon scale really clearly. And it essentially acts as a strict multiplier against the target weight. Let me see if I have the mechanism right.
All right.
If you have a target weight of 100 pounds for a block, and epsilon is set to 0.01, the algorithm calculates 100 times 1.01.
Correct.
So the absolute maximum allowed weight is 101 pounds. It will physically reject any configuration that tries to pack 102 pounds into that block.
That is the exact mathematical check happening under the hood. The algorithm keeps a running tally of the weight.
Right.
Every time it considers moving a vertex into a partition, it checks that tally against the epsilon limit. If the proposed move exceeds the target weight multiplied by 1 plus epsilon, the move is supposed to be blocked.
So a 0.01 epsilon means only a 1% imbalance is allowed. Extremely strict. A 0.05 epsilon allows a moderate 5% variance. 0.10 is relaxed at 10%. And an epsilon of 0.50 means the system is basically taking the day off, allowing a massive 50% imbalance.
Yeah, pretty much. But the crucial takeaway is that epsilon isn't just a suggestion. In mathematical optimization, a constraint is a hard wall. Meaning if the wall is breached, the entire output is categorically invalid.
Which sets the stage perfectly. Let's introduce the 3 algorithmic contestants stepping into the ring to handle these high-stakes partitioning tasks.
The showdown.
Exactly. First up, we have TKPT TTN-TSHP. This is the modern newcomer. It's built on C++20. It's fully active open source under an MIT license, and it comes with all the modern testing and integration bells and whistles you'd expect today.
A very strong contemporary contender, built with, modern software engineering practices in mind.
Then, in the opposite corner, we have HMetis. This is the dinosaur of the group.
Oh, definitely a dinosaur.
It's written in C, and get this, it was last updated in 1998. It requires outdated 32-bit compatibility layers just to run.
Yeah, it's incredibly old.
And to even use it, you have to punch in these cryptic, zero default, 9-positional argument command line calls.
It is a total relic from another era of computing. Yet, remarkably, it is still cited and used in research today because of its historical footprint.
Unbelievable. And finally, our third contender is Kai-Hi-Par. This is the heavyweight champion of pure cut quality.
Right.
It's built on C++17, has Python bindings for easy access, it's multi-threaded, and has a highly active development community.
So we have the modern tool, the 1998 dinosaur, and the heavyweight champion.
Now let's trigger the trap. The researcher behind our source document sets up a deliberate, completely impossible test case, just to see how these 3 programs behave when the laws of physics are broken.
This is the best part.
Here are the exact parameters. The total weight of all the vertices in the data set is 10,000,004. We're going to divide it into 2 parts, so the ideal perfect balance is 5,000,002 per part.
Right. And the epsilon, the allowed wiggle room, is set incredibly strict at 0.0000001.
That is practically zero tolerance for imbalance.
Absolute zero.
But the data set contains a poison pill. Inside this web of 10,000,004 points, there is a single massive vertex weighing exactly 10 million.
Yeah.
And by the fundamental rules of graph theory, a single vertex cannot be split.
It is the 10,000-pound boulder from your earlier analogy. It physically cannot fit into the 5,000-pound space the epsilon constraint demands.
It just can't.
It is mathematically guaranteed to fail.
What's fascinating here is how each of these 3 software tools reacts when handed this impossible task.
Yeah.
The source visualizes their terminal outputs side by side.
And the differences are chilling. Let's look at the newcomer first, TPTKN-CPP.
Okay, what does it do?
It provides what the author calls the clear signal. It explicitly outputs a textual warning stating that the balance constraint is violated.
So it actually admits it failed.
Exactly. It shows its work, printing out part 1 has a weight of 10 million, which is greater than the maximum allowed 5 million. It throws a bright red flag on the play.
Then we check the heavyweight champ, Kai-Hi-Par. The researcher labels this the confusing middle.
Why is that?
It actually prints out an intermediate warning during its local search process. But in its final official output summary, it just relies on raw numbers.
Oh,
Yeah, it spits out imbalance 0.999999 without any explicit final text warning saying the constraint actually failed.
Wow. So it provides the data, but it requires the user to manually interpret the severity of that data in the final readout.
Right. It doesn't formally declare a failure state at the end.
And then we reach HMetis, the 1998 dinosaur. The author calls this the silent failure.
What happens?
HMetis completes the run in a fraction of a second. It completely ignores the imbalance constraint, and it silently returns an invalid result with absolutely no warning whatsoever.
You're kidding. Nothing.
Nothing. It just prints its cut score and says done.
It packs the 10,000-pound boulder into the 5,000-pound truck,
Yeah.
completely ignoring the suspension braking, and hands you the keys as if it just performed a miracle.
Exactly.
Okay, I have to push back here, because I think this is the crucial question you, the listener, might be asking right now.
Sure, go ahead.
So HMETIS doesn't give a bright flashing text warning. Why is that such a catastrophic big deal? Doesn't the user, who is likely, a highly educated data scientist or engineer, just look at the final partition numbers, see that one block has 10 million and the other has 4, and realize it's imbalanced?
Well, that assumption is precisely what causes so much silent damage in modern scientific computing.
Really?
Yes, it leads us directly into what the author terms the instant answer fallacy. There's a brilliant, somewhat cynical quote in the deck.
Let's hear it.
If you just need an answer no matter correct or not, I can give you a program that runs within 0.0000001 seconds.
Because it's just printing random garbage fast.
Yes. Fast and output producing does not equal valid. You have to remember the scale we are dealing with. In modern scientific computing, these algorithms aren't run once by a human sitting at a desk thoughtfully reviewing a single output log.
Oh, right. They're automated.
They are embedded deep inside massive automated pipelines. They are run millions of times a day.
Ah, I see. A script is just scraping the final cut score and moving on to the next task. The human never even sees the logs.
Exactly. Without an explicit machine-readable error code or warning that halts the pipeline, a fast, silent failure is completely indistinguishable to the supervising software from a valid algorithmic breakthrough.
So if these black boxes are failing silently in automated pipelines, the author must be proposing some sort of diagnostic standard to fix it.
They are.
Like a legally binding contract for the software, where it's forced to confess if it breaks the rules.
That is a perfect way to phrase it, and it's exactly what the author introduces, the rigorous answer contract. Historically, we've treated these algorithms as opaque black boxes.
Input goes in, output comes out.
Right. You assume the black box did its job.
But the rigorous answer contract changes the software's job description.
It shifts the software from being a mere calculator to being a diagnostic filter.
Okay, how does that work?
The contract demands a mathematical guarantee of one of two outcomes. Either it provides a fully valid partition that respects all epsilon constraints,
Or
it provides a best effort result paired with a giant, unavoidable warning flag that explicitly registers as a failure to the supervising system.
so it can't just pretend it worked.
Right.
Hmm.
That explicit warning is the fundamental difference between guesswork and accountable science.
The slide deck has a really ominous diagram illustrating what happens when you violate that contract. It's called the scientific integrity problem.
Oh, the ripple effect.
Yeah, it's a ripple effect, starting from that one missing HMETIS warning. First, you get false confidence. The pipeline assumes the output is valid.
Mm-hmm.
That leads to non-reproducible runs, because the algorithm is silently breaking the rules differently on different hardware.
Which is a nightmare for researchers.
Totally. Which then creates invalid benchmarks that actually get published in academic papers.
And finally, you arrive at wrong conclusions. You have entire fields of downstream research, millions of dollars of grant money, building cutting-edge theories on a foundation that is mathematically contaminated.
It is literally the reproducibility crisis happening in real time.
It really is.
Now, here's where it gets really interesting. If human scientists and basic scripts can be fooled by a silent failure, what happens when we hand this broken HMINIS algorithm over to a highly advanced artificial intelligence system?
Oh boy. This is where the consequences escalate from bad data to active sabotage.
Active sabotage.
Yes, specifically in the realm of reinforcement learning, or RL parameter tuning.
Okay, to make reinforcement learning tangible, let's think about training a puppy. You want the puppy to sit. When it sits, you give it a treat, a reward.
A classic analogy.
Right. The AI is the puppy. It's constantly tweaking the settings of our partitioning algorithm, trying to find the magic configuration that yields the lowest cut score, the fewest wires severed. When it gets a low cut, the system gives it a digital treat.
But the reward mechanism isn't just based on the cut. It has to enforce the rules.
Right. So imagine you tell the puppy to sit, but instead the puppy figures out a way to magically steal the treats out of your pocket while running around the room.
Ah.
If the algorithm silently fails, like HMETIS, ignoring the balance limit, but still prints out a fantastic low-cut score, the AI gets the treat without doing the work. The puppy learns a terrible habit.
Your analogy maps flawlessly to the specific mathematics outlined in the sources. The author details the RL objective equation, labeled as R sub t.
Okay.
In a healthy system, the AI's dashboard calculates the reward by taking the good cut score and then mathematically subtracting a massive penalty if the balance constraint is violated.
So if the AI tries to cheat and dumps all the transistors into one block, the penalty wipes out the reward.
And the AI learns not to do that again.
Makes sense.
Under normal circumstances, yes. But in a contaminated reward loop, which is what happens when you plug HMetis into an AI pipeline, that penalty equation is just bypassed.
Bypass completely.
Yes, because HMetis fails silently and reports 0 constraint violations.
What?
So the balance penalty effectively multiplies by 0. It vanishes.
Wow.
The AI's dashboard only says the incredibly low cut score.
Hold on. Let me make sure I'm fully grasping the math here.
Yeah.
If the penalty is hidden, why does the author say the AI specifically drives the epsilon dial down to 0? Wouldn't the AI just leave epsilon alone since the penalty is gone and it's already getting treats?
Well, that is the really insidious part of how these AI agents search for solutions.
How so?
The RL agent is exploring a massive landscape of parameters. Tighter epsilon constraints usually represent a mathematically harder problem.
Okay, yeah.
So if the AI stumbles into a configuration with an incredibly tight epsilon, say 0.001, and the underlying algorithm silently ignores that constraint and returns a perfect cut score.
Oh, I see where this is going.
The AI's reward function interprets that as a monumental achievement. It essentially thinks, I just solved the hardest possible version of this problem perfectly.
Oh, wow.
So it greedily optimizes in that direction, pushing the epsilon tighter and tighter to maximize its apparent success.
So it's actively optimizing for delusion. It thinks it's a genius manipulating the fabric of space and time, when in reality it's just exploiting a broken software latch.
It is a mathematical hallucination, and the real-world cost of this is staggering. The sources emphasize that researchers end up wasting months of incredibly expensive GPU time on supercomputers. Months. They let these AI agents run for weeks, consuming massive amounts of electricity, converging on entirely useless, physically impossible configurations. All of that time, money, and energy burned simply because a console warning was missing at the very bottom of the software stack.
Months of wasted supercomputer time just because a program from 1998 didn't want to admit it couldn't lift a 10,000-pound boulder?
Pretty much.
Which brings us to the final act of our showdown. Given the sheer danger of silent failures and contaminated AI loops, how do researchers actually navigate this today?
It's tricky.
I mean, if I'm starting a massive machine learning company tomorrow, I assume I'm just banning HMetis entirely and forcing everyone to use the modern CTNMP and CTP tool, right?
You would think so, but it's not quite that simple. Context is everything in research. The author provides a very pragmatic ecosystem health and scenarios matrix to navigate this.
Okay.
And it reveals some surprising nuances about legacy software.
Let's test that out. What if a research team is trying to reproduce the exact results of a seminal paper published back in, say, 2005?
In that specific scenario, for legacy or historical compatibility, the author concedes you actually have to use HMetis.
Even though it's broken?
Yes. If you are trying to perfectly recreate a 20-year-old experiment, you need the 20-year-old tool, flaws and all. However, the author explicitly flags it in bright red. HMetis is completely unsafe for any new development.
That makes sense. You can't verify history if you change the instruments. Okay, what about a team doing pure academic research?
What's their goal?
Say they don't care about automated pipelines. They just want the absolute highest quality benchmark cuts, and they have the time to be meticulous.
For maximum quality benchmarks, the recommendation is the heavyweight champion, KaiPar. It consistently generates the highest quality cuts and has excellent multi-threaded performance.
But wait, didn't KaiPar have that confusing middle warning issue?
It does. Because its terminal outputs can be vague, it requires the research team to manually implement strict mathematical constraint checking on the final outputs. You can't just trust it, you have to manually verify its homework.
Which leaves us with the automated future. Someone spinning up a brand new project, specifically an auto-tuning pipeline using reinforcement learning.
For new projects and RL pipelines, the definitive recommendation is CKP-TT-NCP. It is the only tool deemed safe for automated learning.
Because it actually passes modern software engineering checks. Looking at the author's code quality report card, CKP-TT-NCP utilizes modern build systems like CMake. It has robust testing frameworks like Doctist, and it integrates with GitHub Actions.
It is healthy, living software. Unlike HMetis, which has no tests, no modern build system, and zero issue tracking.
If we connect this to the bigger picture, CKP-TT-NCPP is the only tool recommended for AI pipelines, precisely because it honors the rigorous answer contract.
Yes. When the AI pushes it to do something impossible, it throws an explicit, impossible to miss warning that triggers the balance penalty in the AI's math.
forcing the AI to learn the right way.
Exactly.
So what does this all mean? Summarizing the bottom line of this entire slide deck, a simple text warning in a software console is not just a nice-to-have cosmetic feature.
No, it's not.
It is essential infrastructure for scientific reproducibility. Without it, you aren't doing science. You're just generating very fast random numbers.
It is the bedrock of trust in computational research. If the tool cannot tell you when it fails, you can never truly trust it when it succeeds.
That's a great way to put it.
An answer without a guarantee of integrity is just a guess dressed up as data.
Which is a remarkably heavy thought. And it brings me to something I want you, the listener, to mull over as we wrap up this deep dive.
Oh, interesting.
Think about your own life and the software, the apps, the highly automated systems you interact with every single day.
We use a lot of them.
We really do. We live in a society that is completely surrounded by machines designed to give us instant answers. We type a query into a search bar, we ask a digital voice assistant a question, we click a button to generate an itinerary, and boom, an answer appears instantaneously. But based on the mathematical hallucinations we've unpacked today, I want you to ask yourself, what silent failures are hiding behind your screen right now?
That's a scary thought.
When your GPS reroutes you around traffic, or an automated financial app approves a strict budget, or a generative AI drafts an important email for you, are you actually getting a valid, thoroughly constrained result?
Or are you just getting a really fast answer from a machine that simply hasn't been programmed with a way to admit it failed?
Exactly. The next time a piece of technology hands you a perfectly neat answer to a deeply complex problem, start looking for the warnings.
Question the epsilon.
Yes. Wonder about the epsilon constraints operating invisibly in the background. Because if there's one thing we've learned from the hypergraph partitioning showdown, it's that true precision isn't about a computer never making a mistake.
It's about honesty.
Right. It's about having a system honest enough to tell you when the scale is fundamentally broken.
Absolutely.
Keep questioning the black boxes in your life. And thank you for joining us on this deep dive.